No, yes, it's quite empty today. Even emptier than yesterday.
Yesterday. Comparatively.
Relative. Compared to the first lab?
No.
Πώς δεν είναι? Okay. Please.
Is it good? Okay. All right. Okay, let's get started. As usual, we have fewer people on Fridays, huh? They're the most dedicated folks. So today I plan to finish GPU architectures. We started it yesterday, and we finished most of it. And before that, we covered SIMD, array and vector processors. We'll finish that, and then we'll move to memory. So the remaining, I think 5 + 1, 6 lectures, 5.5 lectures are going to be on memory. If we had a 26 lecture, which we don't this semester, that would also be on memory. And I will motivate why we're going to study memory, because it's really the most important bottleneck today. Okay, but before we get ahead of ourselves, let's do the GPU architectures part. And this is an important part because for people who really care about the exam, some of you might, we have actually questions on GPUs on the exam. And I like a particular style of question, which I will show here, which you will have on your exercise also. Okay, so GPUs are graphics processing units. Initially, they were designed for graphics. There were a lot of GPU graphics libraries that were created in the even early as 1980s and the 1990s. And then people started saying, oh, there's this graphics processor that I have in my system. Can I do something with it? Can I do some computation with it? So they started tweaking the graphics libraries. They started actually trying to accelerate programs. And they figured out how to use the GPUs to accelerate things that are more massively parallel, that are similar to, that basically fit this sort of programming model that we discussed yesterday, SPMD. And over time, this movement, let's say, kind of grew, and people said, okay, we can use GPUs for general purpose programs. There were papers written. There were people actually demonstrating that you can actually do a lot of scientific computation on GPUs that exist on in your laptop or in your desktop. And over time, people said basically, oh, we could use this hardware to be more general purpose, right? And over time also, at the same time, GPU vendors figured out that oh, we can actually make this more general purpose because people are using our hardware for general purpose stuff, not just graphics, right? So over time, GPU hardware became more and more parallel as well, and less specialized in the sense that there are clearly graphics-oriented things that we didn't talk about inside the GPUs, like for textures, etc. There are specialized cores, special functional units for graphics computations. Those are not being used as much, but the general purpose cores that we've been discussing have become used by a lot of people. And GPU vendors also started making those more general purpose, easier to program, etc. And as a result, GPUs became very popular. And as we discussed in an earlier lecture, some folks started using GPUs for machine learning training at some point and also inference. And they figured out that these are very capable, and that enabled deep neural networks to be actually quite sustainable today with general purpose hardware. And that's what really enabled GPUs to take off over time. So you can see this is an example of a specialized, more or less specialized hardware that is available for accelerating graphics over time being adopted to become more general purpose. And today it's quite general purpose actually. GPUs are quite general purpose as long as you can write programs nicely using this SPMD model. So that gives me a nice segue into what we discussed yesterday. As we discussed, we distinguished between programming model and execution model. And GPUs are programmed using SPMD programming model, single procedure or program multiple data. And essentially, I gave you the example of, for example, counting the characters in a book, right? I'm not going to give you the same example, but that's a very good example. You divide the program into many threads, and each thread counts 10 pages, and each thread actually does essentially the same thing. It executes the same program on different pages, right? So basically, you have multiple instruction streams, threads, that execute the same program, but they work on different data, and they can execute a different control flow path at runtime. So we're going to see that different control flow path. Yesterday, I gave the example that maybe one thread has only A's, right? Only characters A's, character A in 10 pages, which is a weird page, of course. But another thread may have actually all types of characters in 10 pages. So these clearly update different locations in the histograms that they're updating. And as a result, they take different paths, right? Okay, and as we discussed, many scientific applications are programmed using this SPMD model. And usually, especially in the past, people used multiprocessors, multiple processors, MIMD hardware, multiple instruction, multiple data, for accelerating large-scale scientific applications. So you can actually have many cores, many general-purpose processors executing the same thread at the same time. GPUs make it much better in the sense that if threads are doing exactly the same thing, why decode the same instruction many times, right? If you're using multiprocessors, they're executing the same threads. Each of them is decoding the same instruction, scalar threads. Each of them is decoding the same instruction many times, the number of threads times essentially. Whereas GPUs, as we discussed, it's programmed on SIMD hardware. It's an SPMD programming model. And if threads are at the same program counter, you take that instruction, decode it only once, fetch it only once, execute it only once, and perform the operation on many different data that is specified by the different threads. So that's the benefit of the SIMD hardware to execute the SPMD model. Okay, we also distinguished yesterday between SIMD and SIMT a little bit. Basically, if you have SIMD, each instruction is a vector instruction. We got rid of that with the SIMT model. You have multiple instruction streams of scalar instructions now in GPUs. Essentially, this is a scalar set of instructions. If you remember the code we went over yesterday, it had 4 instructions. And you specify the number of threads, you don't need to deal with the vector length of hardware. And we discussed yesterday that you can actually treat each thread separately, meaning you can do MIMD processing, and you can do fine-grained multi-threading of warps. So if you remember that, we discussed that yesterday. I'm not going to discuss it again. But today I'm going to show you some things that you can do if you have this sort of execution model, meaning if you have different scalar threads and you have the capability of grouping threads that are at the same program counter together into a warp, so that you can actually improve your utilization in the hardware. So let's take a look at an example. Let's assume that this is our thread. We see some blocks over here that need to be executed. And you can see that clearly there's some conditional control flow, meaning sometimes after A, you go to B, Sometimes you go to F, depending on how the branch calculates, let's say. And here, when you execute, the threads can execute different control flow paths. For example, thread 1 starts from the same program counter. All threads start from the same program counter, which is the beginning of this block A. There may be multiple instructions in A, but the block ends with a branch, as you can see. This is a control flow graph, as we have seen in the past. Thread 2 may take a slightly different path. Mostly they're taking the same path, thread 1 and thread 2, but at some point they diverge, as you can see, which is after B. Thread 3 takes the same path as thread 2, as you can see, so that's good. Thread 4 takes a mostly different path, as you can see. It goes through AFG. Now, assume that at the beginning, they are part of the same warp, because they're at the same program counter. How would you execute something like this on GPU hardware? GPUs that can actually execute this, except they're not extremely efficient. They're going to, depending on which PC a thread is in, they're going to execute only that thread if it's supposed to execute that program counter. So we'll see this. Hopefully it'll become clear, but this is the example we're going to kind of follow quickly. Essentially, we use scalar threads and group them into warps, right? Actually, we're going to see a simpler example. Basically, what I showed you earlier is branch divergence. When threads inside a warp branch to different execution paths, you have multiple threads in a warp starting at the same program counter, but at some point they execute a branch. They all execute this branch, but some of them go to path A, some of them go to path B. What the GPU does dynamically at this point is create two warps. One warp goes and executes the instructions on path A. The other warp goes and executes instructions on path B. And to be able to do that, GPU creates a mask, and the mask is dependent on the result of the branch. Basically, whichever threads should go and execute path A, the bit vector that's associated with the warp is set to 1 for those threads. For all of the other threads that are not supposed to execute on path A, the bit vector is set to 0. So you actually take the warp over there, execute all the threads, but ignore the results for those threads for which the mask is set to 0. And you do the same thing, or you do the opposite thing for path B. The threads that are taking path B, their mask is set to 1. The threads that are not taking path B in the warp, their mask is set to 0. And you execute path B, and you make sure that the threads whose masks are set to 0, they don't update the register file, for example. That's the idea, basically. So let's take a look at this pictorially, if you will. Initially, assume that you have 8 threads in a warp. Initially, all of them are at the same program counter, which is here. They all come to the branch, and it turns out some of them take path A. You can see that 4 of them, the condition of the branch evaluates such that they should go through path A. So only 4 of them are active, if you will, or their mask bit is set to 1 for this program counter that specifies path A. So GPU executes them, writes the results, etc. And then GPU executes threads that go to path B, which is really the complement. The mask is really the complement of the mask over here, as you can see. Only these threads, these 4 threads, execute path B. So this is another warp. So GPU dynamically creates 2 warps, as you can see, right? One warp has 4 active threads over here, and the other warp has the complement of those 4 active threads over here. They both execute separately, but while the hardware executes these 4 active threads, you have 8 lanes in the GPU. You're really utilizing only 50% of your GPU, if you think about it, or the SIMD unit, or this particular processor in the GPU. And when you're executing this path, path B, you're also utilizing the 50% of your execution unit. So branches actually reduce utilization, as you can see, in a GPU, which hopefully makes sense. And then there's hardware in the GPU that detects that these paths merge, and then the GPU dynamically merges these two warps it has created to a single warp and executes all of the threads with a mask of all ones. If you think about it, here, if all of the threads are executing that particular program counter, the mask is all ones. Otherwise, the mask can have zeros. Okay? So hopefully this is clear. It's very interesting, right? It's a very interesting model. But we have seen this before, if you think about it. When we talked about vector processing, this is why GPUs are vector hardware, essentially. This is the same as conditional or masked execution, right? We talked about masked execution. We basically create a vector mask based on a condition testing. And essentially what the GPU does is that. Based on a branch instruction, it creates a mask, and it decides which of the data elements should be executed on for that particular program counter. So it's very similar to what we have seen with vector processing. Okay, recall the vector mask and masked vector operations. If you don't recall, it's on the slides from the SIMD lectures. Okay, so this was an example of how you dynamically create warps. The question is, of course, if you are able to do this, can you do even more? And we're going to see this is a very simple control flow graph, as you can see, right? This was a more complicated control flow graph. We're going to get back to it. So let's see what happens, or what could happen in this complicated control flow graph. Can we actually add some hardware and make GPUs more efficient when they're executing complicated control flow graphs? Okay, so basically, this is what this says. You can group threads into warps flexibly. I showed an example of this, but you can actually do more than what I showed. Essentially, if you have many threads, many warps, you can find individual threads that are at the same program counter, group them together into a single warp dynamically, and this reduces divergence, improves SIMD utilization. This is one of my favorite questions, as you will see later on. SIMD utilization is really the fraction of SIMD lanes executing a useful operation. As we have seen in the previous example, when you have four active threads within a single warp of 8 possible threads, 50% is the utilization rate. Okay, so essentially executing an active thread. So basically, people also have figured out that you could do this dynamically among a pool of many threads. You can dynamically merge threads executing the same instruction, in other words, at the same PC after branch divergence. You can form new warps from warps that are waiting. Because as I said yesterday, you don't just have warps that are executing inside the pipeline, you also have a pool of warps that are waiting, that are put on the GPU, that are registers allocated on the GPU, and they can be scheduled. Why do we have a larger pool than the number of pipeline stages that you have in a GPU? Because some of the threads may actually go to memory and wait. So you actually, GPUs actually have many threads, many more threads than the number of stages in the pipeline. It could be hundreds, as I said yesterday. You don't have 100 stages in the pipeline. So there are some warps that are waiting to be executed. Whenever you have time, or whenever you have a stall, you basically schedule them inside the GPU. So essentially, enough threads branching to each path enables the creation of full new warps. I'm going to give an example of this. Let's take a look at warp X and warp Y. Warp X has 4 threads, the blue threads over here that are active. The rest are inactive. And warp Y has the orange threads that are active, and the rest are inactive. You can combine these two to look like this. That looks easier than said. It's easier said than done, but it's possible, right? You know that they're both at the same program counter. You just need to have some merging logic, combinational logic that figures this out and combines these two warps. Now, you can only do this if the arrows don't clash with each other, right? Because if the arrows, if warp Y, for example, had a thread over here at lane 0, remember we partitioned the register file across lanes, they cannot go, 2 threads cannot be on the same lane at the same time, right? So you're going to see this again. I'm going to ask you that question again. So this happens nicely. It's kind of like fill in the blanks, right? If you can actually have multiple warps that can fill each other's blanks, you can group them together because they execute using different lanes in the SIMD units and using different register sets. Okay, so this is another example which basically shows what I just said. Here, this is warp X, let's say. This is warp Y. It turns out warp Y has 2 orange threads over here that overlap on the same lane with the blue threads. As a result, you can merge some of these things, some of these orange threads that don't overlap with the blue threads into a single warp. You can improve the utilization of this warp, as you can see. But unfortunately, you still need to have a warp to execute the 2 threads that are conflicting in the lanes with the blue threads. Hopefully that makes sense, right? I'm going to give you another example of this with the control flow example that we saw. But you may say, okay, it's a bad idea. We didn't gain anything. On average, our utilization is bad. On average, the utilization of the thing on the left over here is the same as the utilization of the thing on the right over here, right? On average, that's true. But if you had one more thread over here, one more warp over here, you could merge that nicely also. Makes sense now, right? So basically now you can calculate the utilization of this. Here you have an almost full warp. Utilization is 7/8. Here it's 6/8. No, that's also 7/8. So it's 7/8 on average. And you can figure out what this is by calculating. So basically, we saved some time and also improved our SIMD utilization. So this works if you have enough threads that are waiting, as you can see. If you had only these two, you wouldn't save much. Okay. Okay, let's take a look at an example over here. This is GPUs do things like this, which is nice, I think. Let's take a look at how this code is executed. You have these blue. Initially, this is the simpler code. We're going to look at the more complicated code as well. Initially, you have all of the threads executing this program counter. You get to a branch. Some of them, they take path A. And then let's say you have another set of threads that are fetched that execute this program counter again. This is another warp, let's say. They all take the branch as well. Remember, we're doing fine-grained interleaving of warps. And then it happens that the threads that are blue and orange take path A over here. And you can merge some of these. So this is what I showed you earlier, kind of. You couldn't eliminate this one. But you could eliminate maybe something on path B, but it doesn't work very well here. But that's the idea, basically. When you get to path A, you can merge things like this. And if you have more threads coming into the GPU that are executing path A, you could merge even more. Okay, so let's go through this example over here. This is a little bit more complicated, but if you look over here, we're going to look at the execution of warp X. So we're going to have two warps, X and Y, and blue one will be denoting X, and the orange one, or maybe this is kind of red one will be denoting Y. And this A means that warp X is executing basic block A. Imagine basic block being a single instruction, but it could be multiple instructions also. In this case, all four threads are active in the warp, right? We're going to look at a warp size of 4, just for simplicity. And we're going to see the benefit of dynamic warp formation compared to the baseline. Baseline doesn't merge the warps together. I'm going to just animate the baseline. So you can follow this on your own or right now. But this is basically the execution path threads take. So initially, if you look at A, both warps all are full. They have 4 threads, and they execute A. And then some of them go to B from warp X, and some of them go to B from warp Y. You can see that the utilization is 3/4 over here, whereas it's 2/4. But some of them, and then some of them go to C from warp A, and some of them go to C from warp Y. You can see that utilization becomes even lower because you're going nested in the control flow graph. And these also show you the mask, which threads are active from warp A and which threads are active from warp B. Initially, all threads are active. You lose one thread from warp A over here because one of them goes over here, as you can see. And you lose 2 threads from warp Y over here because 2 of them go over here, as you can see. And then you lose one more thread over here. Essentially, only one thread from warp X goes to C, and only one thread from warp Y goes to also C. You can see that from here. And you know exactly which thread based on the mask. Right? This is what the GPU does, actually. It looks at the masks. And you can also see that D is similar. So only 2 threads from warp X are at D, and only 1 thread from warp Y are at D. And similarly, F and Y, you can basically you can look at every single one of these. Okay, so this is the execution. In the end, when you get to merging points, threads get merged back into their warps, and eventually threads become full, as you can see over here. At G, for example, all threads merge at this point, and the warps become full again. And then you go back to A, and then they're full, and then they diverge based on the data that they have again. Hopefully this makes sense. You're executing this control flow path based on different data elements. So different threads are doing different things because their data elements are different. Okay, if you do dynamic warp formation, you can create a new warp from scalar threads of both warp X and Y executing at basic block. And we're going to look at that. Initially, these threads are full, so there's no reason to do anything with them. You can see that B, there are 2 warps that are executing B. Now you can merge this 3 with one of these over here because they align nicely. There's an empty slot over here, empty lane, if you will, in this warp. Unfortunately, you don't eliminate an execution cycle, let's say. So this warp has to execute with one thread because you couldn't merge these two. And then you can merge these C. These two warps are both executing C, which is the same instruction. And you can merge these two nicely. So you eliminated one of the C's, as you can see, which is nice. And then these two warps are also executing D, and then you can eliminate both one of them because they happen to align nicely. And then E, unfortunately, you cannot eliminate completely. Well, you cannot eliminate one completely. And then F, again, you can eliminate one of them. So hopefully you got the idea right. And the point is, if you do all of this, now you executed the same work in a shorter time, right? As opposed to going, let's say, until here to execute everything, you went until here. With additional hardware cost, of course, there needs to be hardware to merge these threads from different warps to a single warp, and then also to distribute them back at some point. Does that sound good? We're not going into exactly how the hardware is implemented, but it's implemented using some sort of logic that takes into account masks and PCs, etc. You can imagine that, actually. You should be able to implement it with enough thinking, with enough knowledge about what is going on over here. Okay, so hopefully that's interesting. So you can see how sophisticated modern GPUs are. There's actually a lot more that goes on that we didn't talk about, but I'll give you a couple more quickly, and then we're going to move on. Any questions? Okay, no questions. Okay, so as I said, you cannot group things flexibly, meaning if two threads from two different warps are in the same lane, you cannot put them together. And the reason you cannot put them together is because of this. Essentially, different lanes have different register sets partitioned. So if you have thread IDs that are at the 0th lane, that happen to map to the 0th lane, you cannot execute them at the same time because only one thread can be accessing the register file at a given cycle, right, over here. And but if they go to different lanes, then you can actually put them, merge them with another warp that doesn't have a thread in that particular lane. So that's the idea over here. The hardware is not flexible enough to merge everything. You can, of course, add hardware to move a thread from one lane to another lane, but that's very, very difficult. That kind of goes against the single instruction multiple data principles, because we're operating on single instruction multiple data. Otherwise, you need actually really a large network to enable that. Okay, so as I mentioned, we like questions on GPUs. This is an example question that I'm not going to talk about in detail, but basically, we can give you some code, very similar to what we have seen earlier, maybe slightly different. And we ask you, what is the utilization? Basically, how many warps does it take to execute a program like this, based on some, let's say, information that is provided in the question. For example, a warp in the GPU consists of 32 threads. There are 32 SIMD lanes. Each thread executes a single iteration, very similar to what we have discussed, right? And then we describe the arrays, etc. And then we can ask you, assume the condition of this if statement is this. What is the number of instructions in the body for the SIMD utilization to be X? Right. This sort of question is interesting because it tests your understanding of whether you really understand how a GPU works. And I'll let you deal with it because it's fun. So I really think that this is fun, actually. Take a look. You will have similar questions in your optional homeworks as well as exams, past exams. Right. Okay, so let's move on. I'm going to give you very quickly a couple of other ideas that actually made their way into modern GPUs. There are a lot of interesting ideas that are actually in GPUs, but let me give you a couple of other things. Essentially, GPUs are underutilized because of branch divergence, as we discussed, right? But also long latency operations, and this is also going to be important for memory again, right? So one thing you see is in the GPU, you may have a lot of warps, and if all of the warps are doing the same thing, which is the case if they're at the same PC, and if you have this SPMD programming model, they also happen to hit the same long latency instruction at the same time, meaning all of them come to a load and that load misses because you're starting, let's say, a new phase of execution for some reason, and you don't have the data in the caches or scratchpad, etc. So what happens in a GPU is all of them send requests to the memory system and you wait. you kind of waste a lot of cycles waiting for data to come back from memory, essentially, which is going to be the subject of the next part of today's lecture. We're going to try to solve that problem better. But let's take a look at how you can solve this problem with better scheduling. And then after some point, the data for all warps come back, and all warps start computing again. So this is what happens if you do scheduling of all warps in a very, let's say, large manner, in the sense that you send one warp down the pipeline, another warp down the pipeline, another warp down the pipeline. They all start from the same program counter, and they hit the same long latency load that are around the same time, essentially. Now, what we have proposed in this paper that we wrote about 15 years ago is something that I like, and that's actually implemented. There are better versions of it implemented in existing GPUs. What you do is basically, you don't have all the warps doing the same thing. What you do is you have a smaller group of warps compute and actually make a lot of progress for those warps, and they hit the load earlier. And then you set another group, let's call them group 1, go ahead. So you make more progress in group 0 first, hit the long latency load, get to it earlier, and then you make progress, you start executing group 1 next, and then group 1 hits the long latency load a little bit later, as you can see. So if you do that, what happens is group 0 started its memory requests earlier, so they will arrive a little bit earlier, as opposed to waiting for all of the warps to actually hit the memory or get a cache miss, let's say, at the same time. So group 0 can start computation when it's memory requests, when it's fewer memory requests come back from memory earlier. This way, again, you save cycles, as you can see. So as opposed to being very homogeneous in how you actually treat all of the warps, chunk the warps into smaller groups such that they all make, let's say, a little bit different progress, as opposed to making the same amount of progress. That's the idea over here. There are many, many other ideas that build on this idea. So it's very fascinating how GPUs do scheduling. But this simple idea actually improves performance significantly. In many cases, more than 20, 30%. In some cases, even more. So it depends on, of course, how you do the scheduling, etc. So you can actually cover for a lot of these latencies. Okay, there's another idea. You can play a lot of tricks. I will not go into this in detail, but if you can have a large warp, this is kind of, let's say, we have a large warp over here. Each warp, let's say, the execution width of a GPU is, let's say, warp size is 4 threads. Each warp has 4 threads. We call it like micro warp. And then a large warp may be much larger, actually. In this case, like, I think it's 8 over here. So you have 32 over here. And then you see the active masks of each of the smaller warps over here. If you have this picture nicely, what you can do is you can basically figure out from these smaller warps which threads are active, and then form a warp that is actually mostly utilized. And you can again figure out which threads are active over here and form a warp that's mostly utilized, and then figure out what threads are active and then form a warp that's mostly utilized. So this is actually very similar to what I described earlier, but a different way of implementing it. So you can see that if you have a bigger picture of which threads are at which location, this is assuming that all of them are at the same program counter, of course, you can utilize your pipeline nicely with a lot of active threads in different warps. There's only one slot that's wasted over here because you don't have enough, let's say, threads that are executing at that lane. Okay, so if this was not clear, that's okay. But this is very similar to what we have described earlier. So if you're interested, there's a lot of work in this area. This is old work. There are newer works also, but old works are also quite interesting. Okay, any questions? I'm done with GPUs. I just want to give you some examples of real GPUs right now before we move to memory system. Again, how many people have programmed GPUs here? Okay, not many people. How many people want to program GPUs now? Okay, more people want to program, that's right. Well, if you can program, then you can actually get a lot of potential benefit in terms of performance improvements. Okay, let's take a look at an example GPU. And this is kind of going to be historical also, because GPUs improved a lot, as I said, over time. And today, with actually very data-intensive workloads, they're improving even more. So this is a very old GPU, I think from 2008 or 2009 or so. It essentially looked like it had 240 stream processors. Essentially, NVIDIA calls a stream processor as a SIMD functional unit, which is a weird way of thinking about it. Basically, you have 8 SIMD functional units per core, and 30 cores. You can think of it that way. So this is what it looks like. This is a core from NVIDIA terminology. You have essentially 8 functional units over here, and there's some control clearly that's shared across these 8 units, decoding, for example, and there's a huge amount of registers so that you can actually keep track of the number of threads over here. So this is one core, and at the time in 2009, okay, I think essentially a group of 32 threads share the instruction stream. Each group is a warp, as we discussed. They execute the same instruction on different data, and up to 32 warps are interleaved in a fine-grained multi-threaded manner. So this was a small number. So you have 8 functional units, but 32 warps are interleaved in a fine-grained manner. And up to 1024 thread context can be stored. So you really can have 1024 threads over here. Okay, so, and you can see the thread context storage is large. And that's one core. This was the architecture at the time. Again, we're talking about 16 years ago. You have 30 cores, 30,000 threads. We're much larger today. 30,000 is a large number, but we're much larger today. Okay, so that was GTX 285, 2009, assuming the date is correct, which I'm not sure, but this is from NVIDIA. So basically, things improved over time. I'm going to give you like some improvements, not everything, of course. Clearly, things improved on the internet, but as the computation capability improved, also the memory capability improved. So you can see an example over here. This doesn't end at the current time, but you can see that the number of functional units increased a lot over time. The gigaflops performance has increased over time significantly also. So this is V100, which is, you can place it to 2017, assuming this is correct. So you have a lot more cores right now, 80 cores, and each core is more capable, 64 SIMD units, as opposed to 8. So it's much wider right now, as you can see. And NVIDIA decided to add tensor cores for machine learning, which essentially are floating point multiply and accumulate units that are more specialized to do multiply and accumulate in floating point. I'm going to show you that also. But basically, this is bigger. Caches are bigger, memory is bigger, etc. And you can see the 80 cores over here. And you can see that the numbers have grown significantly also in terms of the types of operations you can do. Let me give you a very quick overview of the tensor core at the time. This is like 6-7 years ago again. So basically, it's a floating point based tensor core. It does multiply and accumulate. So you can actually use this tensor core to do matrix vector, matrix multiplication in the floating point data type. This is going to improve also for machine learning. This was introduced for machine learning, and it's going to improve even more, as we will see. Okay, if you are interested in the tensor core, again, I don't want to go into a lot of detail, and I'm not going to ask you questions about this. It's just NVIDIA's tensor core. But if you look at a tensor core, it's also a SIMD unit. Basically, it's a parallel SIMD unit. It has specialized instructions like 4x4 matrix multiply and accumulate every cycle. You can do that. So it's a very specialized instruction to speed up matrix multiplication, essentially. And one thing that's interesting over here is register contents can be shared across different threads inside the warp. So you can actually do some things interesting, like accumulation operations nicely inside a single warp across different threads. So this helps some operations in machine learning, which is very interesting. So we have seen systolic arrays. So this is these tensor cores are actually kind of competitors to systolic arrays. I will not go through the systolic arrays again, but this is Google's Edge TPU. It kind of has a systolic array processing elements over here. And its goal is to essentially do matrix multiplication also. And we've seen an example of this when we covered systolic arrays. So if you're interested, you can take a look at it. And we also looked at this a lot. So if you're interested in this Edge TPU, which is a systolic array approach as opposed to a SIMD approach, you can look at it. And you remember the lecture from there. So the reason I bring up systolic arrays is the different approach from SIMD, right? I'm going to leave you with that question at the end of this part of the lecture soon. Which one's better for machine learning? So NVIDIA is clearly taking the approach of SIMD. They don't have a lot of systolic arrays, whereas Google is taking the approach of systolic array, and they don't have a whole lot of SIMD in their architectures. But there might be combinations that are better, actually, but we're not going to go into that. Okay, so this is a newer generation. I forgot the time. This is maybe 2020. I don't know, something like that. And you can see that the cores are increasing. 64 SIMD function units per core are there. So it's becoming more powerful. And tensor cores are also becoming interesting. Basically, and the caches are becoming bigger, which we'll talk about in the next lecture. Essentially, the tensor core is more sophisticated now. What it does is it has a different, let's say, data type that is actually better for machine learning, and clearly compilers need to take into account. But they have support for sparsity also. Sparsity means in machine learning and in a lot of applications, your matrices may have a lot of zero values because some of your weights are all zeros, right? For example, and multiplying by zero is kind of a waste, right? If you do a full multiplication with a zero, and we have discussed this actually a long time ago when we talked about scheduling instructions, right? Multiplying by zero is easy. Why do you actually do the full multiply? Why are you taking 8 cycles to do a multiply? In this case, you can actually do even better if you can encode your matrix such that you kind of get rid of the zeros. So this is a matrix with a lot of zeros. Zeros are white ones. Non-zeros are green ones. You have an encoding of the matrix, compressed format of a matrix, where you encode only the green ones and then store the indices of where the non-zero elements are. Then you can actually have a much more, let's say, condensed form of storage for the matrix. You don't waste a lot of memory. You do a little bit more computation to figure out what actually needs to be computed on based on the index of the element. So basically you say the element at row 0 and column 0 is not a 0, so operate on it. Right? The element at row 5, column 200 is not a 0, operate on it. That's what this index means, right? As opposed to storing zeros. So it's a different format. And this tensor core can now operate on this format so that it gets rid of unnecessary multiplications by zeros. Does that make sense? This is called sparse tensor cores in general. Essentially, in general, sparsity means that you have some things that you don't need to operate on. You have a lot of zeros. In fact, this is actually very interesting because if you represent, for example, a very large graph. For example, I have a very large graph. I represent my who do I know in the world? That's a huge graph. It's a very sparse graph, right? Out of 9 billion people in the world, I don't know how many I know, right? Let's assume that I know 10,000, and that's probably an overestimate. 10,000 out of 9 billion. Everything else is zeros, right? So that's sparsity for you. So that graph is very sparse, and encoding it with a lot of zeros wastes space. Encoding it this way saves space, plus saves energy and performance, and improves performance. Okay, so that's the idea of this sparse tensor core. Okay, and then now we actually updated this graph over here. This is H100 over here, and you can see that it's growing, and also memory is growing. So now we have 144 cores in H100. That's 2022, and a bigger cache, etc. And now tensor cores are becoming more sophisticated also. People have figured out that how do I save energy? How do I improve performance? Okay, sparsity is one thing, but I'm operating on huge data elements, 32-bit data elements, floating point or whatever, tensor floating point, etc. So let's actually cut that down. Let's make our machine learning models train using smaller data elements. For example, you can see FP8 over here. This is becoming lower and lower actually over time. And that way we can save a lot of energy when we actually use the smaller data elements, right? Because you're not doing computation on 32 bits, you're doing computation on 8 bits. Increasingly, this is going to become 4 bits, 2 bits, maybe 1 bit, let's say. Then you can actually enable many, many other interesting things. But you can see that there's a lot of support for different types of data. There's still FP32 support because you need to keep that. So tensor cores are becoming more complicated, but also they have support for data types so that they can save energy and improve performance when that energy saving happens. Okay, this is the most recent, and again, things are increasing. Since we're going to segue into the memory lecture, memory is also increasing. So there's a very high memory bandwidth in this particular GPU with high bandwidth memory. I'm going to show you an example of what that may look like soon. And you have a lot of memory also compared to a GPU, for a GPU essentially. Okay, so this picture I showed you earlier, I'm not going to go through that. So there's a lot of interesting things going on in the GPU space that we're not going to talk about, more than this at least. Let's see where we are. We're almost at time. So basically, it's good to think about this, right? We covered a lot of models so far. And GPUs and systolic arrays are the last 2 type of models we covered. It's always good to ask the question, which one's better for different applications, right? Which one would you use for machine learning? Which one would you use for different type of applications, image processing, graph processing. What types of parallelism does each exploit? You should be able to answer that question because we know how they exploit parallelism and what are the trade-offs. Again, I don't expect you to answer these questions over here because there are a lot of interesting questions that people in industry are also trying to tackle. And also, as you can see, that they're trying to do things such that they're not necessarily bound by a particular model. For example, the tensor cores that are introduced are not necessarily completely bound by purely SIMD execution, right? Over time, people actually change how things work also, right? There's still SIMD-ness over there, but there's a lot of also specialization that happens so that you can customize for matrix multiplication, for example. Okay, so if you're interested in such questions, you can certainly take our later courses. And one thing I would recommend if you like GPUs is our heterogeneous systems course. We have a lot of lectures on GPU programming. You can watch them on your own. And I will mention the bachelor seminar in computer architecture again. For those of you who are really interested in doing this, you can take it. And there are some slides over here. And we have also research opportunities. Okay, so I think I'm going to end early for the earlier part of the lecture. Any questions on GPUs? No? All sounds good? Okay, so let's be back when the bell rings. And then we're going to start a whole new chapter, which is the memory. And I'm going to motivate you for memory first. Okay, let's get started now. So now we're going to switch gears and talk about memory. I'm going to go through some slides relatively quickly to motivate you why we're talking about memory, because this is so important. But we're running a bit late given that we have one lecture kind of eaten away. So I will try to get to the organization and technology. But before that, you have another opportunity for an extra credit. Since we talked about Amdahl's law, now I can review Amdahl's paper, which not many people review. Please write a one-page review, no LLM use, no ChatGPT. Those tend to be very, very, let's say, superficial in general. But if you can fool us, maybe that's your challenge. This is more of the honor code, not clearly. Honor code is good. Okay, you have the deadline, etc. So these are some readings for this lecture and next. You can see some recommended readings. You can find them. So basically, before we jump into this, essentially, we're done with execution models. We're done with a lot of interesting things. These are all compute-centric models. We covered a lot of processing paradigms. Now you're familiar with many of them, which is good. It's good to think about the trade-offs of these processing paradigms. And I kind of finished the last lecture with that, right? Systolic arrays versus GPUs versus FPGAs potentially, right? So it's good to think about that. And some of these paradigms cross across the layers, right? Like GPUs, for example, have programming as well as execution parts. Okay, so basically what determines the widespread success of a paradigm is something good to think about as well, right? All of the paradigms that we discussed actually are used today for different purposes. Sometimes they are combined. So it's good to think about that. Again, these are more philosophical things at this point, but also it's good to think about adoption. Now let's take a step back. Basically, I showed you this slide at some point. You have computation, communication, storage, and memory. You looked at a lot of computation components, even though we sprinkled in some registers, memory at some point. We're going to now look at storage and memory, which is actually, there's a lot of communication, like interconnects over there as well. So basically, we're going to cover memory a lot. Memory is critically important. So why are we going to talk a lot about memory? Normally, I dedicate more than 6 lectures to memory. We're going to be, I think, 5.5 this time. Let's see. But it's important because it's most of our system. So this is 2006, AMD's flagship multi-core. If you look at this, there are a lot of caches over here. If you look at a core, there are a lot of caches inside there. There's a register file. All of those are actually memory. And then once you go out there, memory controllers, memory interfaces, memory banks. And then once you go out there, storage, etc. And I was showing you a lot of pictures over time. A lot of these systems are actually memory. Inside each, let's say, core, you have a lot of memory. Outside, you have a lot of memory also. Okay, this is actually a picture that I like. What we're missing, right? We usually look at a processor chip. A processor chip also has a lot of SRAM in general. We're going to talk about SRAM, DRAM. And then there's DRAM, and then there's the darkness that a lot of people forget, storage. That's usually why you buy your phones, for example, because you can actually store a lot of stuff. And that's a different type of memory. These are all different types of memories, SRAM, DRAM, storage. And we're going to see some of those. These are some old systems. Memories were not always, caches were not always on chip. This is just to make you think. Because we can put, because of Moore's law, again, whose paper you reviewed at some point, we are able to put many transistors on a single chip. So caches started becoming part of the processor chip. So processor chip actually started eating a lot of other chips that are in the system because we are able to integrate much better using fabrication technologies that we have. So this is Intel Pentium 4 system, which has an on-chip cache, right? Caches were not on chip. We're going to see caches later. And this is a more recent system with a lot of caches. So this green part is all caches, basically. And then there's a memory interface. So you can see that memory in a single node or single chip is growing. So if you look at this system over here, this is all cache. There's a lot of cache inside these cores. This is memory interconnect. And then there's system management unit, which is a lot of memory. So most of the chip is really memory. And the numbers are growing. And people are putting more memory. On top of this, you can stack another chip with a lot of memory, which is interesting. This is another chip from IBM, a lot of memory, basically. Most of the outer peripherals of the chip is really for accessing outside memories, outside devices, etc. So you can see memory signaling, for example, over here, which is a huge part of the chip. As we discussed earlier, you need to communicate with the outside world. And when you need to communicate with the outside world, let's say memory, you need to have large I/O pins, input-output pins. And these are really, really large mixed signal structures, digital plus analog structures, and they're quite expensive. Okay, this is a GPU. I'm going to skip some of these, but the point is there's a lot of memory. In this chip also, there's a lot of memory, right? The reason these folks built this chip is so that they can have a lot of on-chip memory, right? This is 40 gigabytes, which is pretty large, and there are a lot of memory bandwidth so that you can actually supply that memory to the computation. It's relatively fast. Okay, this is my picture. This is actually interesting. I drew this picture in 2008. And my point was actually to show that most of the system is really dedicated to memory structures, memory and interconnect. Yet we're still bottlenecked by memory. So now I'm going to show you some data showing that. Essentially, memory is really critical for performance. We've seen this many times in this course at the very small scale, and now we're going to look at the larger scale a little bit. For example, we talked about load-related stalls and pipelining, right? You could not really forward data from a load and a dependent add that's coming out right after it because of the way we structured the pipeline. Even that is related to memory, right? Load store handling, out-of-order execution, memory latency tolerance. One of the reasons out-of-order execution is so good is because memory latencies are long. We talked about VLIWs, let's say Achilles heel, right? We have long latency memory operations. We talked about VLIW compilers, etc. briefly. We talked about many memory banks needed in SIMD processors because you unleash a lot of memory operations, right? We talked about GPU register files more recently and high bandwidth memory systems. We're going to see more and more of that. You need modern systolic arrays, you need high bandwidth memory. You have seen that in the real systolic array example. So even systolic arrays whose purpose was to actually reduce the memory bandwidth requirements need very high bandwidth memory because there's a lot of data they still need to stream inside the systolic array, right? If you remember that. And we use fine-grained multi-threading, for example, to tolerate memory latency in GPU. So you've seen a lot of this, these examples in the course. Now we're going to look at how the memory is designed. And one of the reasons is really applications. So I'm going to give you some examples very, very quickly again. There are a lot of applications today that are very, very data intensive. I've given you multiple examples before, like machine learning, genomics, data analytics, graph analytics. And essentially, we're able to generate a lot of data in the world today, right? And we need more analyses on the data. So this is one example. I kind of showed you this picture multiple times in a different way. But essentially, memory requirements are growing, for example, for neural networks, large language models. If you look at this picture, and if you believe it, this is mostly believable, let's say, there's a 4 orders of magnitude increase in memory requirements in just a few years, because people have actually improved the models such that they can digest a lot of that data. Of course, it takes a lot of time, but memory requirements are growing. At the same time, compute requirements are growing also exponentially. Okay, so just to give you the application perspective, there are a lot of applications. These are some references. If you're really so inclined, you can look at the references. These references essentially show that a lot of these applications that we use in data centers, et cetera, or daily lives are really bottlenecked by memory. I'm going to give you some numbers soon. These are some other applications that we have actually studied in some of our work a lot. And they're also bottlenecked by memory. And if you look at other applications like genome sequencing, this is an area that I like doing research in. How can you accelerate genome sequencing extremely fast and extremely efficiently, such that you can have devices that you can hold and sequence your genomes, and you can distribute those devices across the world, let's say, so that people can actually do something useful with these devices for their own personal health or for collective health, etc. So this genome analysis is also very much bottlenecked by memory in the end. Again, I'm giving you a very high-level picture because clearly you don't need to know about genome analysis for this course, but the point is a lot of these applications need a lot of data, and in the end, storing that data, moving that data, processing that data leads to a big bottleneck. Now, let me give you some numbers. This is actually interesting because this is from a chief architect of alpha processors, Dick Seitz. This person led a team that designed processors that competed with Intel at the time. They were faster than Intel's processors. Actually, you've seen an example of this, Alpha 21264, when we talk about out-of-order execution. It was the first 500 megahertz processor of its time. When they designed one of these flagship processors, he decided he would write a paper. This is a one-page paper. If you're interested, you can read it. And it's titled, It's the Memory, Stupid. Basically, they designed this processor to be extremely fast. They did their best. And they designed this for particular database type of applications, let's say. It's general purpose, but their goal was to really accelerate data-intensive applications. And in the end, he wrote this paper saying that this processor is capable of finishing 4 instructions every clock cycle. Clock cycle is short, and 4 instructions is superscalar, right? At the time, we're talking about 1990s. Unfortunately, on this important workload, set of workloads that we think we designed it for, it's finishing 1 instruction every 4.7 cycles, every 5 cycles, let's say. So it's not finishing 4 instructions per cycle, it's finishing 1 instruction every 5 cycles, meaning it's operating at 5% of its peak throughput. Why? It's waiting for data to come back from memory, even though it has huge caches for the time being. And basically, he ends this article saying that I expect that over the coming decade, memory subsystem design will be the only is his emphasis, important design issue for microprocessors. So you can see the importance of memory, right? These people who design these processors say, it's all about the memory. Okay, I agree with that because I did my PhD thesis on this topic, but this is data that we collected with Intel across hundreds of workloads. And we found out that essentially all those hundreds of workloads, most of the time, a flagship processor is waiting for memory most of the time. This is average data. Okay, you can read papers, etc. This is Google's data from 2015. Again, Google analyzed all of their data center workloads, and according to their analysis, most of the time, the processor that they have, a flagship processor, again, top of the line processor in their data centers is waiting for memory. It's finishing instructions, like retiring instructions, committing instructions, only 10 to 20% of the time. That's the green part over here. Now you know what retirement means, right? We've covered all of that in processor design. So most of the time it's waiting for memory, and they have more analysis in the paper if you're interested. So it's very fascinating, right? We're designing these processors, yet most of the time they're waiting and doing, let's say, nothing useful from the perspective of finishing instructions. So that's performance. Let's talk about energy. Energy is even worse. If you look at data movement versus computation energy, this is data from NVIDIA. It's old data. Things have improved a little bit, but the relatives remain the same. So if you look at an arithmetic operation, 64-bit double precision arithmetic operation, it's cheap, 20 picojoules only, even at the time. A memory access, a DRAM access is 16 nanojoules. So the difference between those is 800x if you do the calculation. And there are other numbers over here, which even an SRAM access, a small SRAM access is 50 picojoules, more costly than computation, as you can see, right? Going from this end of the chip to this end of the chip to communicate data is 1 nanojoules compared to 20 picojoules. So computation, an expensive computation, 64-bit computation, is still much cheaper than communicating data, accessing memory. Why is it so high over here? Because you need to go off chip. You need to exercise interconnects that are large and big. So a lot of energy is spent on those interconnects. A lot of energy is spent on the DRAM chip, etc. Right? Okay, so that's the difference. Essentially, today a memory access is actually around 100 times more costly in terms of energy than a complex addition. And as we discussed in the earlier lecture, people don't want complex additions, right? Complex additions are expensive in terms of throughput and energy. So we want simpler additions. So if you compare a 32-bit integer addition to a DRAM access, assuming the numbers, the disparity becomes 6400x. So the energy cost of memory access is much worse compared to a relatively simple addition, 32 bits. As we discussed, people actually want to reduce those additions to 4 bits, 2 bits, 1 bit ideally. And that reduces the computation cost. That doesn't reduce the memory access cost as much. So this disparity is going to increase and increase. Okay, so just to give you a perspective, right? And we're still talking about main memory over here. If you go to storage, like an SSD, multiply that number, 6400, by another 10x at least. So to bring data from storage all the way into the processor, you're consuming 64,000x the energy it takes to do a 32-bit addition. It's good to ask the question at this point, does it really make sense to move the data all the way to do a very simple, energy-simple operation? I'm wasting a lot of data, moving data back and forth, right? I'm wasting a lot of energy, moving data back and forth and back and forth. Okay, so this is just to give you the perspective from, and there's a lot of works that show this. Okay, we did a lot of work also to quantify the effect of this on energy in systems. On average use cases in a mobile device, if you're doing, for example, if you're using YouTube, or if you're doing Chrome browsing, or if you're doing video encoding and decoding, or TensorFlow inference, most of the time, most of the system energy is spent on data movements, moving data back and forth, basically. This is a small number. And you've seen this before also. If you actually have even an accelerator that accelerates machine learning, for example, and your machine learning model is reasonably large, not as large as what we have today, more than 90% of the total energy in your system is spent on accessing memory. So that's why we look at a lot into processing in memory, basically. As opposed to moving the data from memory to the processor, why not do the processing inside the memory? Right? Put the processor inside the memory. And there are different ways of doing that, which I'm not going to discuss. But this is actually fascinating. Change the paradigm a little bit. Don't be processor-centric. Okay, so let me give you another perspective, which you have seen if you actually reviewed my talk, which was the extra credit assignment. I'll go through this relatively quickly also. But essentially, memory is also critical for reliability. If you look at the data in the field, a lot of the errors that happen in a system are caused by memory. Because a bit in memory fails and you get a wrong result, or a bit in memory fails, or multiple bits in memory fail. As a result, the system needs to stop. You need to do some repairing, etc. We analyze this a lot with industry as well as with our own infrastructure. And we found out that essentially a lot of error rates are increasing. As memory becomes denser and denser, as you put more memory chips in a system, and it becomes denser and denser, memory becomes much more vulnerable to noise effects because the cells are smaller. We'll see some of these cells later on. And cells are, many cells are around cells. As a result, you get actually a lot of errors. So if you're interested, again, there are a lot of papers on this topic. So we build a lot of infrastructure in my group. These are some of the infrastructures. I'll go through these also relatively quickly, but you're using FPGAs. They're much more capable FPGAs than what you're using. And with those FPGAs, you can actually do testing of memory. Just to show you some pretty pictures, we build a lot of these controllers, etc., to understand some of these issues with memory in terms of performance as well as scaling and reliability. So you can see that there are a lot of FPGAs that we look at. These are all different types of FPGAs, actually. And this is our laboratory. We actually have a lab that tests a lot of memory, understands. We build a lot of infrastructure. But this is how, for example, we discovered the RowHammer effect in memory, which you may have seen in the if you've done the extra credit assignment. How many people have done the extra credit assignment here? So, okay, you know the RowHammer effect. I'm not going to talk about that. But this is an effect that happens in real world, and people are actually designing chips to fix this effect, right? So, okay, I'll go through this relatively quickly. And people, this is a security problem, as you have seen in the extra credit assignment also. Okay, so basically, memory is also critical. My point is, memory is critical for performance, clearly. That's why we talked a lot about performance. There's also energy, but it's also critical for security, safety, and robustness. It's not just about the processor, basically. We often tend to forget. Actually, if you're taking an old-fashioned, let's say, computer architecture class, you would not be talking about memory much. I don't like that sort of class because that gives a very, let's say, lopsided, one-sided picture of how things are today, right? If you go into the field today, you will be talking about memory. How am I going to solve this memory bottleneck? Every day you will be thinking about how am I going to solve this memory bottleneck? Even if you're designing processors, your task would be memory, essentially. Even if you're writing software, assuming you care about performance, of course. Okay, basically, all of these slides were to motivate that memory is really critical for computing. It's really critical for lots of things, right? I didn't talk about some of these things. Cost. Cost is also important. If you look at a data center cost today, most of it is really memory chips. Because people want more and more memory chips, more than 50% in a large server. In some cases, more than 80% if the memory is much larger, right? If you really have a data-intensive application. Form factor, again, memory occupies a lot of space today, which is important for carbon, again. Today, we care about sustainability a lot more than we did care about it 10 years ago. And certainly, sustainability was not really on the radar of computing 30 years ago, right? But today, we care about how much carbon that we waste to actually produce these chips, to actually keep these chips around. So it's really important to think about these. So that's why we're going to dedicate, let's say, 6 lectures or so on memory. But now I'm going to start with fundamentals, which is going to be the organization and technology. So we're going to kind of build from bottom up, just like we did with processing, right? But you have seen some of the memory, so some of this will be familiar. But I'm going to give you a larger perspective of how, for example, a DRAM system looks like. And then we're going to go more into caches and memory hierarchy next week. So if you think about it, memory looks like this from a programmer's perspective, right? You have some array that's specified by the ISA, and you do loads and stores to it, right? That's what you do from a processor perspective again. So this is an abstraction, meaning it is true that the memory doesn't look like it like this, but there's another level of abstraction over here, which is virtual memory. How many people know about virtual memory here? Okay, not many, so you're going to learn, but maybe some of you know. What programmer sees as virtual memory, and you're going to learn that in the last lecture probably, more. Programmer can assume the memory is infinite, basically. The reality is that physical memory size is much smaller than what the programmer assumes. So we provide this abstraction to the programmer such that the system, meaning system software and hardware cooperatively, maps virtual addresses to physical memory. So there's a translation layer that happens. And this translation is not pure software, not pure hardware. It's really a combination of software and hardware working together to enable this view to the programmer. So this system automatically manages the physical memory space transparently to the programmer, and this has enabled a lot of things, as we will see in the virtual memory lecture. So for example, the programmer does not need to know the physical size of memory. They don't need to manage it. They don't need to worry about, oh, does my program fit in physical memory? Or does my data fit in physical memory? They don't need to worry about any of that. The system automatically does that. A small physical memory can appear as a huge one to the programmer, and as a result, life is easier for the programmer. Right? Whenever you make programmer not care about something underlying, that's good. You improve their productivity. But of course, you take away something from the programmer, and now the programmer cannot manage the memory by themselves. So if they're actually really good at managing memory, they cannot. Right? They can perhaps do better than what this system could do if they know their application really well, right? So they need to work even harder to do that now. So that's the flip side. Every design decision that you make is a trade-off, right? There's no good design decision for every single metric that you think about. Okay, so the downside, another downside of this is now you have more complex system software and architecture, microarchitecture. This is a classic example of the programmer microarchitect trade-off that has been extremely successful. All systems we have today have virtual memory, all, really almost all. But basically, the trade-off is made such that architecture is more complex. Microarchitect's life is harder, as we will see in the virtual memory lecture. Programmer's life is easier. Programmer meaning the user programmer or application programmer, not the system programmer. System programmer deals a lot with figuring out how the virtual memory works. Okay, so this requires indirection and mapping between virtual and physical address spaces. So you have a virtual address space that's kind of fake, if you will, and then the real physical address space, physical memory where the data is actually stored. And there needs to be some indirection and mapping to enable this. So we're going to see this a lot, but this is a really important piece. Now we're going to talk about the physical memory system. So forget about virtual part. We're going to talk about how this is, let's say, constructed. So you need a larger level of storage to manage a small amount of physical memory automatically. So physical memory almost always has a backing store, disk. And we will first start with this physical memory system, and we're going to ignore the abstraction, but we will get back to it. So let's take a look at this idealism. So we looked a lot into instruction execution, pipeline, and we tried hard to make performance better. We didn't talk about everything over here, but we talked about a lot of things. Pipeline stalls a lot, for example. How do you actually handle dependencies? Interconnect, ideally, it should be zero cycle. Ideally, you have a lot of functional units to exploit parallelism, as we have discussed in the GPU lectures. Ideally, computation should take zero latency, right? That's idealism over here. Instruction supply and data supply are mostly about memory system, essentially. Instruction supply, let's go through that. Ideally, you want to access memory with zero latency. You want infinite capacity, especially today. You want zero cost, ideally. And we talked about branch prediction. You want perfect control flow when you supply the instructions, right? Ideally, again. So ideally, data supply also needs to be zero latency, infinite capacity, infinite bandwidth, zero cost, right? That's our goal. But unfortunately, we're not going to get all of those with a single monolithic memory design. So if you look at memory design, if you want huge capacity, you need a huge decoder, right? Immediately, there's a capacity latency trade-off, right? If you want to access, let's say, a terabyte of memory, your address becomes log 2 to the 1 terabyte, and then that's a huge address. And to decode that address, you need to build a huge decoder, as we discussed, right, in decoder lectures. So basically, this is what ideal memory is. I added energy over here also. Zero access time, infinite capacity, zero cost, infinite bandwidth, zero energy. Unfortunately, we're going to have a trade-off. This is the reason why we're going to build a memory hierarchy as well. This is also the reason why we will build our memories to be, let's say, more hierarchical. So you start with a simple array, you put multiple arrays together and expose that as a bigger array, even though internally the arrays are smaller. And then you put multiple arrays together and expose as a bigger array, even though internally, it's like snowflakes, right? If you have a snowflake, and if you look at any point, it looks like a snowflake internally, right? This is going to be similar. You have an array. Internally, if you focus on it, there are more arrays. Internally, you focus on each array, there are more arrays. You focus on it, eventually you get to the cells, right? Basically, it's going to be a hierarchical design of many arrays with, eventually you go to the cells, basically. So, okay, what's a memory array? We have seen memory arrays, but let's go into, we've seen, for example, flip-flops, right? I'm going to introduce some more in this lecture. Now go back to lecture 3, 4, 5. So flip-flops are actually very fast, but very expensive. If you remember, one flip-flop cost tens of transistors to us, 20, 30, more, depending on what kind of flip-flop, what kind of latch you have. We're going to look at static RAM. We kind of looked at it very briefly. These are relatively fast, slower than flip-flops, but expensive. 1 bit costs 6+ transistors, as we will see, but better than tens of transistors, as you can see. So you can see now already the trade-off, right? Here, these are large but fast. These are small, like the cells are small, but slower. So dynamic RAM, this is actually most of your memory. These are even slower. These are different technologies, so we will see different technologies. Reading and charge leakage destroys content, so you need to refresh things. And it's going to be interesting. And you need a special process for manufacturing these, because you need a capacitor, actually. So far, we didn't talk about capacitors, right? We talked about transistors, and that was our abstraction. If you want to build really, really cheap memories, you should talk about other technologies, like capacitors. Capacitor stores charge. You can use the charge level in a capacitor to represent whether you're storing a 1 or 0. That's the idea of dynamic RAM, which is really all the main memory that you have in all computers today. But this is very cheap, basically. You can make this capacitor really small and cheap. 1 bit costs only 1 transistor plus 1 capacitor, as we will see later. And then if you want to actually have really, really dense memory technology, you need to go into other things, like flash memory, for example, hard disk and tape. Some of these operate based on magnetic storage principles. Flash memory actually has a transistor, but a special type of transistors. But these are usually much slower. You need very special manufacturing, but they also tend to be non-volatile. Basically, you plug the power off, you still keep the data over there. That's how your SSDs, solid-state drives, work. But these are very cheap. 1 transistor can actually store many bits. Sometimes there are no transistors involved, right? You store charge based on magnetic plates that can be manufactured at very small technology levels. Okay, these are actually very fun, very interesting to look at. But we're going to focus especially on, well, we focused on flip-flops. We're not going to talk about flip-flops. Those are actually what you use in your pipeline, for example, right? Static RAM is what you use to make your register files. A lot of caches are static RAM. Dynamic RAM is your main memory, and then other storage technology is other storage. Okay, so if you look at all of these memories, in the end, they are all organized somewhat similar, meaning they are arrays. Our goal is to efficiently store large amounts of data, even in SRAM, right? Basically, you have an array, you have an address, n-bit address, and you get n-bit of data. So to be able to do that, you need a memory array that stores data, you need some address selection logic that selects 1 row of the array, and you need a readout circuitry that reads the data out. And we're going to look at different types of memories, but the array structure is going to be the same across all memories. So the goal is to have an n-bit value, which can be read or written at each unique n-bit address. Right? Now, all values can be accessed, but only n bits at a time. So there's some access granularity also of memory. Access restriction allows more compact organization of memory because you don't access everything, essentially. Okay, so recall, this is a bigger memory array. This was a bigger memory array that we looked at in the EDCA lecture 5. I don't remember if this number is actually true. This could be from the last year. But one of our lectures in either 4 or 5 this year had this memory. Actually, multiple of our lectures had this sort of picture. But now there's no magic here. This is an array of D flip-flops. So this is a very expensive array. You don't want your main memory to be like this because then you would actually have a huge chip, perhaps, right? If you want 1 terabyte. So now we're going to see how we can construct, let's say, using other technologies. But let's look at these arrays a little bit more. Essentially, these are the arrays. This is an example array with 2-bit address and 3-bit data. You can see that this is actually simple, right? This is actually the same as what we saw over here. But you have 2-dimensional array of bit cells. Each bit cell stores 1 bit. And in this case, you know exactly what the bit cell looks like. This is our bit cell over here. You store 1 bit over here, right? The rest is really address decoder, data out, read out circuitry, the data out multiplexer, etc. And some of these are combined, as you remember, in this circuit. Okay, so an array with n address bits and m data bits, you have 2 to the n rows and m columns. I'll go through this relatively quickly because it's kind of obvious. We've seen this, but just to jog your memory from earlier lectures, you have a number of rows. This could be number of words also. You have number of columns. This could also be referred to as word size. And array size is clearly rows times columns, right? 2 to the n times m in this case. So this is our simple array. And we kind of have seen this, so I will not go through this. You can basically figure out what 3-bit data is stored at row 10, right? Okay, so if you want to make an array larger and wider, clearly you need to increase the address size and you need to increase the data size, right? This is another example, 1024 words times 32-bit array. That sounds good, right? And if you actually want to keep larger and larger, you can increase the addresses. But at some point, you need to do banking, as we will discuss, as we have discussed earlier. Okay, so essentially, this is another way of looking at memory. This is also actually going to be interesting because this is how we're going to build DRAM and SRAM cells. This is the address decoder that you have. It's a 2 to the 4 decoder. Again, a simple memory over here. Storage nodes in one column are connected to 1 bit line. You can think of it that way. You have a storage node over here, and then you have another storage node, another storage node. These are connected to the same word line. So if this address is 11, these storage nodes get connected to the bit line 2, bit line 1, and bit line 0. And this address decoder activates only one word line at a time based on the functionality of the decoder. And content of one line is available at storage output. So for example, if you supply address 10, this word line gets activated, and only these 3 bits from these 3 cells that are connected to the same word line supply their data values. So this is, again, a very general way of looking at memory. Now I have stored bit over here, right? I don't talk about what's inside there. It could be a D flip-flop, it could be SRAM, it could be DRAM. And I like this way of looking at memory because all memories are really constructed this way in the end. Okay, now let's take a look at some technology. How do you control the access? So basically, I kind of did not talk about how you control access. Let's take a look at how you control access in SRAM and DRAM. So basically, you can have access transistors that are configured as switches. They connect the bit storage to the bit line. And the access is controlled by the word line. So this is the store bit. This is a generic thing. If you look at this generic thing, DRAM looks kind of like this. You have a word line here. You have a bit line here. This is the DRAM cell. It's a capacitor. And if the word line is enabled, meaning this is the address that's being decoded, this access transistor gets enabled, which means that the capacitor over here shares its charge with the bit line. So there's some sensing circuitry which we will not get into. But what happens is this capacitor perturbs the charge level in the bit line. And there's some sensing circuitry at the bottom, which I'm not showing over here, that senses the perturbation of charge. Right? If this word line is not enabled, this bit line is not connected to the capacitor. As a result, the bit line stays at the level that it was what's usually called pre-charged to in DRAM, a reference level basically. But if this word line gets enabled, the charge from this capacitor gets shared through this RC path, resistance capacitance path, to the bit line. The bit line gets perturbed a little bit because charge flows into it or charge flows out of it, depending on the voltage levels. And as a result, there's some sensing, there's some perturbation in the bit line, and that can be sensed using some sense amplification circuitry. That's the idea of how DRAM operates at a high level, at least, without going into a whole lot of analog detail. That's the insight of how DRAM operates. And the key is you can make this capacitor extremely small. You can make the voltage level at the bit line relatively small, and you can sense very small changes in charge. That's the idea. So people built these DRAM chips today where you can sense very little changes in charge. That's how you can make things denser and denser and denser. But as you make things denser and denser, the charge over here can get perturbed in some other ways, like noise. So that's why the RowHammer, etc., happens also. But now you know how a DRAM operates at a fundamental principle level, right? Maybe you cannot draw the analog operation, but that's not the purpose of this course. The purpose of this course is there's a switch over here, which is the access transistor. And if you actually enable that access transistor, this bit over here can get sensed. If it's charged, it's a 1. If it's discharged, it's a 0. Now you can sense a 1 versus a 0 if you actually design the appropriate circuitry. Okay, let's take a look at SRAM. There could be other different sensing mechanisms, but this is one sensing mechanism. SRAM looks kind of like this. SRAM is a cross-coupled inverter. Remember, we designed this cross-coupled inverter when we talked about sequential logic, and we said that this doesn't work. It doesn't work because there's no setting mechanism or resetting mechanism or reading mechanism. Now we're going to actually set and reset it. Basically, SRAM looks a little bit more complicated. This is a cross-coupled inverter. And now you can have a word line over here, and you can have bit line and bit line bar. So if you enable the word line, in the bit line, you get the value that's over here. And in the bit line bar, you get the value that's over here. And you can actually have some sense amplification, which is easier than DRAM. And you can sense the differences, basically, and you can avoid the noise, etc. This way, you can read out from this cross-coupled inverter that we kind of dismissed in lecture 3, right? I think maybe lecture 2. No, lecture 3. Okay. Hopefully, this makes sense. So now you have 2 access transistors over here. The reason you have 2 is because SRAM uses something called differential sense amplification, meaning you look at bit line bar, you look at bit line, and the sense amplifier becomes easier to design if you have 2 values. It's called differential sense amplification. Again, a lower level concept that we're not going to go into. Yes?
Possible to write?
Yes, that's correct. You can write it also. So we didn't talk about the write circuitry, but there's normally you enable the word line and you have a write driver. So there's some circuitry in the bottom over here that writes the value through the bit line. So you need to supply a value into the bit line and a bit line bar, and then you write it. DRAM also, a very good question. If you want to write to DRAM, for example, what you do is you enable the word line and you set the bit line to high voltage, for example, such that there's some circuitry called, again, write driver. You push a lot of charge into the capacitor. Very good question. I was talking about reads, but there are also writes that are enabled with this. Okay, so if you want to build larger memories, essentially now you know the basic principles of SRAM memory, which is going to be built to, which we're going to use to build caches. And now DRAM memory, which is really main memory. And this is actually everywhere. And then there's flash, which we're not going to get into yet. Okay, let's talk about how to build larger memories. Essentially, you want larger memory arrays. But we know that large is slow, right? Everything needs to scale. You need to have many word lines. If you want to actually go in the horizontal side or vertical side, you need to have many bit lines as well. So it becomes expensive, essentially, and becomes slower. So how do we make the memory large without making it too slow? And you've seen the idea before. Essentially, the idea is to divide the memory into smaller arrays and interconnect the arrays to input-output buses. So essentially, as I said earlier, large memories are always hierarchical array structures. For example, in DRAM, you have a channel, and then you have rank, bank, subarrays, and mats. We're going to show this soon. But essentially, we build on the concept of banking. You've seen this in earlier SIMD lectures. I actually covered it a little bit yesterday also. This is also called interleaving. Essentially, we developed that for a different reason at the time, right? The reason was that actually we want to satisfy one word per cycle throughput from memory. And the memory takes long, each bank takes long. So have multiple banks such that you can start one access to different banks every consecutive cycles. There's another reason for banking, which is really even more fundamental. If you want to have a lower latency access to a very large amount of memory, it takes very long to access that if you build it monolithically. So chop it up into pieces. Each of those pieces are faster to access, right? That's the idea. This clearly is good for latency, but it's also good for what we discussed earlier, multiple access or parallel. Okay, basically the goal is to reduce the latency of memory array access and enable multiple access in parallel. And the idea is to divide a monolithic large array into multiple banks that can each be accessed independently, either in the same cycle or in consecutive cycles. So each bank is clearly smaller than the entire memory storage, and accesses to different banks can be overlapped, as we have seen in earlier lectures, right? So a key issue, as we have also discussed in yesterday's lecture, is how do you map data to different banks? Clearly, what the programmer, the physical memory is really linear, if you think about it. But now the memory is partitioned into these different banks. if you have, for example, 16 banks, 1 terabyte memory, 1 terabyte divided by 16 is the capacity of each bank. It's not as simple as that because we're going to have even more hierarchy, as we will see soon. But where do you put the data, right? Your bank conflicts that we discussed last time, yesterday, becomes a problem. Okay, so this is banking, if you remember again. In our lecture, we looked at banking, and this is one way of building banked memories. And again, all memories are like this. Even if you look at a SRAM cache, there's a lot of banking that happens because SRAM caches are today very large, and you cannot build a fast memory that is really large monolithically. Okay, this is our generalized memory structure. So if you look at this, let's build it from the top down over here. You normally have a memory controller. This is actually DRAM specific. You have a channel, and you have a bunch of memory DIMMs, as we will see. Let's call them a rank. We're going to specify these later on. And each rank has, let's say, 4 chips over here. So you can think of this as what you would plug in to your DIMM slots in a machine. If you've ever designed your machine, you have DIMM slots, and you put memory modules, right? This is called a module, but it's also called a rank. A module can have multiple ranks, as we will see, but let's call it a rank. A rank has multiple chips over here. So if you look at each chip, it has multiple banks. And this is a bank. If you look at a bank, it has a 2-dimensional array of columns and rows. But we will see soon that internally, that's also smaller arrays. Even this bank is too small, so you actually have smaller arrays, what's called mats soon. So okay, this is another picture. Again, I will not go through this, but you can look at these pictures. Before I move forward with a little bit more detail, I'll have to take a look at the time. Okay, let's see. I will foreshadow what we're going to talk about also. But basically, today people are able to put logic and memory on top of each other also. This is what high bandwidth memory is. If you have ever wondered about high bandwidth memory, you actually have a logic layer under memory layers. And this logic layer has very high bandwidth access to memory because you have a lot of interconnects between the logic and memory. Again, I'm not going to talk about that right now, but let me give you the top-down view of the DRAM system, and then we're going to finish this lecture. It's basically, I'm going to build what I showed you earlier. So a DRAM system, as I said, it's hierarchical, right? You start with a channel, which is really connecting a lot of memory modules together. DIMM is a memory module, dual inline memory module. It consists of ranks. It consists in terms of chips. It consists in terms of banks, essentially, and then rows and columns. So this is what a real processor looks like, circa at some point. It has 2 memory channels. Now you can actually have high bandwidth access such that you access potentially 2 channels, right? You can get data from one channel concurrently with another channel. Each channel, if you want to add a lot of memory over there, you can actually connect a lot of these modules, right? So each channel consists of multiple memory modules. Let's take a look at what those memory modules are, essentially. So each memory module looks kind of like this. It has many chips over here. This is actually a real thing. You can look at it. And there's a front and back. This is called a rank. Front is called one rank. The other side is called another rank. Rank is essentially a collection of some number of chips. It could be 8, depending on how much data you want to access concurrently. Again, I will go into it in the next lecture a little bit more. But what is that? How do you access a rank essentially? You can access one rank at a time only. The goal of the rank, the 2 ranks, is to actually buy you more capacity and also some parallelism. But basically, you supply ranks share the address and command bus. So there are these buses. There's the address bus, as we have seen earlier, and there's a command also in DRAM, which we will see soon. And if you want to access data in one rank, rank 0, there is part of the address specifies which rank you're going to address. Right? Physical address you have specifies if it's 0, that means your data is in this rank. If it's 1, that means your data is in this rank. If it's 0, then you need to send the address, remaining part of the address, to rank 0. And you get the data from the bus that's coming out of that rank 0, and then the multiplexer is controlled such that you get the right data from the right rank that you're accessing. So there's no magic again. You have some bits in the address, and the top bit, or 1 bit in the address, specifies which rank that the address is at. Or there's some function that's computed based on the address to figure out which rank you're accessing. So that's a rank. If you look at a rank, internally, a rank consists of many DRAM chips, in this case, 8. Each DRAM chip supplies 8-bit data here. So the rank enables you to get 64 bits of data. Each DRAM chip actually is supplying only 8 bits. So you're sending the same address to different DRAM chips and collecting different pieces of the 64 bits you want to access, right? So 8 pieces of the 8 of these 8 bits get access from data. Let me finish this top-down view, and then we're going to be done. We're almost there. Now, if you look at a chip, the reason this is built this way is because DRAM chips, you don't want very large number of pins in a DRAM chip. This is a very cost-sensitive thing, especially if you want to build large memories. Your chip cannot have a lot of pins. Okay, if you look inside the DRAM chip, now you have many banks because you don't want to have a single monolithic thing because it's slow. So you have 8 banks in this case, and concurrently you can access different banks. You can start an access at consecutive cycles, and each bank can supply 8-bit of data, right? So in one cycle you get 1 8 bits, in the next cycle you get another 8 bits, another 8 bits, another 8 bits. Now if you go to each bank, it looks like a 2-dimensional array of rows and columns, and you've kind of seen this already. It could be 32,000 rows in one array, for example. It could be 2 kilobytes in the total columns. And then if you want to get 1 byte, you need to multiplex. There is a big multiplexer over here. You access a row, which brings the entire row into the sense amplifier's row buffer. This could be 2 kilobytes. And you select which byte you're going to access based on the address bits. Okay? Okay, so we're going to stop here, but this is the abstraction level. This is the bank abstraction level. We're going to break it down also because this is still too large. If you want to build fast memories, this is still too large. You don't want to have an array structure of 32,000 to 16,000, let's say, because if you multiply 2 kilobytes by 8, you get 16,000, right? So we're going to build it even with even smaller arrays going into the future. Well, future meaning next week. Okay, hopefully this was interesting. We're going to start at this point next time, and we're going to actually build memory hierarchies out of both DRAM and SRAM, and we're going to have a lot of fun. Have a good weekend. I'll see you all next week.